So in about 10 seconds, I think that's the buffering time. The video should be live. If you could confirm that beforehand.
Yes, it's working.
Okay, perfect. Then hello everybody, welcome to the November Ada Meetup. And as always, thank you for coming here. And today we will have a very interesting presentation about Ironclad and, well, maybe the distribution galore. Hopefully I pronounced that correctly. And I think we can just get started. So if Strake, if you would like to present us Ironclad.
Surely. Hello, everyone. I am Christian. I go in the internet by the name of Strixu. And today I wanted to make a little presentation about Ironclad, which is a hobby operating system kernel, which I have been working on for the last 1.5 to 2 years on and off. I'm gonna now start talking about the project. What is Ironclad, first of all? Ironclad is POSIX compatible, formal verified to an extent. Formal verification is a huge can of worms, which we will talk about later. It offers her real-time facilities and flexible scheduling. A really big part of what makes Ironclad special is the suitability to her real-time tasks while not forgetting general purpose computing. It is highly portable. It's ported to several architectures. The main port right now is x86, which is the architecture I'm most comfortable with personally. There are some ports to other architectures like Raspberry Pi 2 B boards, Leon 3, which is an aerospace-oriented chip in the Spark architecture. I've not been able to get my hands on one of those yet, so my testing on that front is in virtualization software. And there are also ports to things like the Virt targets in ART64 virtual machines. And the big selling point of the operating system kernel is that it's free software from front to back. It's something like 97% fully GPL Ada, with the remaining percents being held by some assembly code, also GPL, and things like build system scripts. So it's a fully Ada, fully free software operating system under the GPL license. The goals of Ironclad is first and foremost to create a highly secure architecture. As we will dive in later, a big selling point and a big emphasis in Ironclad is done in things like making sure the integrity of userline code. And as it was said earlier, have real-time suitability without compromising general purpose computing. In terms of the scale of kernels, when we think about kernels, I like to think of two big poles. We have things like free real-time operating system, free RTOS, and at the top we have big monolithic kernels like Linux. With Ironclad, I wanted to place it something more in the middle of the scale, something that people may recognize is filled with QNX and other similar projects. So not something that is meant to run on like the smallest boards, but also something that has some heft and can still fit on mid-range boards and still fulfill tasks that you will have operating systems like Linux make. Well, Linux fulfills, sorry. All of this, keeping in mind POSIX compatibility. Ironclad on itself deviates a bit from POSIX at times, but in the ways that it deviates, it's planned for it to be brought back into POSIX compliance quite easily. These deviations are done for several reasons. Some of them may be for ease of implementation or because, yeah, some things make more sense to make in Ada than others. The operating system architecture, in terms of the operating system architecture, Ironclad is a monolithic kernel. Structure shared by projects like Linux. That means that Ironclad is the only thing fitting in the kernel space, which is represented by things to the left of the red line. and userland either interacts with it directly, programs like GCC, Bash, or Xorg, or it has the option to also go through a libc, like it would be nlibc or glibc. The current distributions of Ironclad run nlibc, mainly because when it comes to porting glibc, it's a horrible project to port. I don't know if any of you have experience with that. It's a massive project with a lot of complexity. So the current distributions use nlibc, and then the libc itself communicates with Ironclad in turn. In Ironclad, given the POSIX deviations that we're talking about earlier, the libc has a really heavy role as kind of the compatibility layer between Ironclad and what is strict POSIX compliance. Inside Ironclad, the architecture is not that interesting either. It's just a mesh of services, think networking, scheduling, interprocess communication, and all of that is exposed to userland through syscalls. So syscalls and sometimes shared memory, which may be used when performance is really critical. But yeah, the main point is that all of the services are held in the kernel. It's not at the microkernel where some of them may be spread through userland. And that has really huge implications when we talk about what makes Ironclad special, which we're gonna do right now. All that I talk right now is not that revolutionary when it comes to operating systems. There are a lot of monolithic kernels out there, a lot of them POSIX compatible. So now what I'm gonna talk about is what actually I think makes Ironclad special, and the things that I really want to further in the Ironclad design. The first thing that I wanted to talk about is mandatory access control, which forms part of the whole security focus that I was talking about that Ironclad has. To that, I wanted to go back to the system architecture diagram of the previous slides and present the case of, as it happens so much in current software development, either because of negligence or because of faulty code or an intruder taking control of an application could turn, I open quotes, evil, as I represented with Xorg and the horns. In normal POSIX systems, depending whether the affected process, the vulnerability or faulty process is held by root, this could very well spell the end of a system and the total loss of integrity. Mandatory access control in Ironclad is one of the methods implemented to make this much harder. Due to how Ironclad is a monolithic kernel and all of the utilities are held in kernel space by it, for an infected program, in this case Xorg, to be able to meaningfully affect the rest of the system, be it corrupt other programs through IPC or delete random files in the file system, it will unbearably need to go through the kernel. Now, Ironclad, whenever it gets a request from any kind of process, what Ironclad does is that it keeps a mandatory access control context, which here I represent by this notepad, where it details what the process can do, along with other information. The important thing about this notepad is that it does not list things that the process cannot do, but it lists the things that the process can do. It's based on the principle of least privilege. And if the process requests to do something that is not in this list, which has items like is shown there, like allocate memory to interprocess communication, access entropies resources, or opening files. And when it comes to opening files, it also owns arrays of which files to open and how to open them. So you can really, how would I say this? You are able to containerize how much of the file system is exposed to a process at a time. By doing this, Ironclad can detect faulty or otherwise compromised processes and deny them that operation, which in a classical POSIX system, if the process was root, it would be by default granted access to everything, and that could as said earlier, spell the end of the system. Now, when Ironclad detects a faulty process, be it for any kind of Mac failure, it allows the system administrator to do a few things with the process. It will immediately stop execution of the process, and it will either allow the operation to fail normally, like it would fail for any kind of other failure, something like an invalid value would also cause failure. It would be another kind of failure, or it can either log it in different login sources or kill the task outright. Well, the process outright, not the task. How this looks in Ada code is very simple. It's basically just a big structure, a context which owns different kinds of data and centralizes them. Things like file filters as their limits. Limits being limit of how big a file can be created, or limits on how much execution time something can get. Capabilities, which is the can change scheduling, can spawn others, can access entropy resources things, and action, which is how to answer to a Mac failure. All of this is mandatory. All processes have them, and they inherit it from their parent. Init, when created, which is the first process of a POSIX system, which goes by PID1, is given what's called a zero Mac context, which is basically a blank check. It allows to do everything. From there, the init optionally can choose to initialize it, and when forking on where assigning that context to child processes, the processes will be able to use that context and be limited that way. A really important thing about mandatory access control in Ironclad, which is a big difference with other mandatory access control schemes, is that in Ironclad, mandatory access control is solely descalatory. That means that once a mandatory access control context is changed to offer less permissions, it can never be brought back up. Another important aspect of Ironclad, and something that is really important as to fulfill both hard real-time and general purpose tasks, is how Ironclad goes about scheduling. In a classic POSIX system, you may have to, well, not may, you do have two schedule entities: the process, which owns a series of threads, along with a memory map that governs them all, and open file descriptor tables, and in the case of Ironclad, also a Mac context, and the threads themselves, which are units of processor execution, which are a set of registers and a stack and little more. In Ironclad, a third entity, which is the actual scalable entity, the thing that the scheduler deals with the most, is introduced, which is the thread cluster. The thread cluster is a group of threads that basically groups several threads regardless of process, and it assigns them some properties, from percentage of total CPU time that they're allowed to things like quanta between threads, policy to use when scheduling between the threads, and whether they're interruptible or not, and other details. This way, taking into account the different clusters, Ironclad can build a total time, whole timeline of how to iterate through the different clusters, and that way accomplish real-time guarantees. If you give a cluster 80% of execution time, each total slice, which will be the total time before the cluster sets are repeated, that way you can ensure that certain processes will run for a certain amount of time. For those of you who have worked on aerospace, this may sound familiar, as it is based on the R-Inc partition scheme, R-Inc being a set of aerospace-oriented standards for distributed systems. And then for the third thing that I wanted to talk about, I wanted to talk about formal verification. When it comes to formal verification, which is a whole kind of worms of itself, as I said earlier, Ironclad is divided on 3 tiers of code. The 3 tiers will be architectural code that is really difficult to verify. Things like processor initialization code or handling the very deep inners of a system. Those things are incredibly hard to verify and do not really provide much value of itself. And well, the second tier would be things that can be reasonably verified, but only to a lesser standard due to either how Spark abstracts state, which makes some abstractions incredibly difficult, thinking about things like page table management, and or other slightly architectural things that either are not worth enough to truly verify to a good level, or are otherwise just not able to be verified to those higher standards. And the third tier being easily verifiable architecture independent code, thinking about things like IPC, IPC cryptographic code, which is the most formal verification intensive, since cryptographic code, you really want to make sure you do that thing right. Things like mandatory access control routines, those things are verified to really high standards and are really the thing that is the most verified in Ironclad, and the thing that has the most emphasis when it comes to formal verification. Formal verification in Ironclad works just like it would work on any Spark data in any Spark code base. It's mostly has the emphasis on absence of runtime errors, and it's accomplished with this use of post conditions, preconditions, global state. And again, it's based mostly on absence of runtime errors and in trying to nail down some global state in order to make sure that we can only interface with certain state on certain points of kernel execution. Here, this example is a basic setUID function where it just has some global contracts in order to make sure that it interfaces only with the process registry logs and to establish the validity of pre and post conditions. Now, given that Ironclad is a monolithic kernel, and given that the syscall mechanism being the main thing that one uses to interface with the kernel, if you run formally verified userland code, you can effectively never leave formal verified code. As in, if the kernel is verified, you only interface with it through syscalls, and the userland code is verified, you can make this positive feedback where you never exit formal verified code, which obviously has massive gains in terms of userland security and how these guarantees of formal verification extend to userland on a syscall by syscall basis. Now, this thing has its complications, of course. Given that Ironclad is a POSIX operating system, which is a choice that was made in order to have good compatibility with existing software, you have to deal with things like certain POSIX syscalls which encapsulate state in a less than optimal way. That's, for example, the case of read, this quite benign looking syscall. If what we want is to encapsulate the state that it requires, we soon run into a nightmare. First, we have to make sure that the buffer memory comes from an appropriate place. We have to make sure that the file descriptor is an appropriate file descriptor, valid file descriptor as well. And all of this can be accomplished by certain formal verification in userland, but then we run into the issue that ensuring where a file descriptor comes from also requires to expose other kernel state, like how that file descriptor was registered. And in this, if the user is not willing to put this massive amount of formal verification and this massive entry-level cost to the formal verification or to make these guarantees of kernel to userland formal verification, it can truly balloon to be something absurd in terms of how much state can be involved in certain syscalls. So before going to other parts of the presentation, I want to say Ironclad on itself is a kernel. And as a kernel, not that different from something like Linux, it requires a suitable distribution to meaningfully run software. This presentation has been so far hosted on Gloire, which is so far the only distribution of Ironclad. It's maintained by me and other contributors. Gloar being an operating system based on the Ironclad kernel and a new userland. As one can see, that's just normal new bash. It's pretty comfortable if one is used to things like average Linux systems. What I wanted to show right now, if I could show this document here a second, okay. I wanted to show a bit of how mandatory access controls works in practice. There is this tool in Gloar called execmac. Execmac will execute a program that you pass in whatever set of mandatory access control conditions you want to execute it in. What we're going to do right now is we're going to execute, given the set UID, memory scheduling, spawn and clock capabilities, telling the kernel that we're gonna want it to log any issue that happens with the flag S. And what we're gonna do is that we're gonna change it to being a root user. And if we now check the permissions that I gave it, I didn't give it permission to execute ptrace. Ptrace being a classical POSIX syscall that allows for debugging of certain processes. You can attach to other processes with ptrace and read information from them, which has been used several times as an attack vector for other in other systems. Now, given that we're a root user, in a classical POSIX environment, there would be absolutely no way to make sure that this would not happen. Once you have root vulnerability in a normal POSIX environment, it's basically game over. strace is a simple program that just lists the syscalls of a running program by using ptrace. If we try to strace something, given that we did not give it ptrace permissions, sorry for the mess of strace ptrace, it's not nomenclature that I chose, but as we can see here, it did not allow it to do so despite being a root user. And if we check the logs of the kernel, well, sorry, if we did something like this, we can check that the kernel indeed reported that there was a MAC failure in PID7, PID7 being strace. If we exit this quick shell, which could have been an SSH shell in a normal system, for example, and we change the policy from S to K, the kernel will instead try to kill any offending process. If we do the same thing and we try to strace again, we will see that the process did not get to report its error. That was because the process was indeed terminated. And if we check again, instead of being a failure, the kernel straight up killed the process. Now, if I can, well, yeah, this is a fully new POSIX system. That's NeoFetch, an application used by a lot of people to show characteristics of the system. And yeah, it's just I just want to show that it's a normal system with no applications and it's running Ironclad. Now, if I can go back to the presentation real quick. Before Ironclad being an operating system kernel in a world of things like Linux, massive projects like Linux or Windows, Ironclad has a lot of work to be done. What we are focusing on the project right now is we want to get a suitable desktop environment to run. We're right now trying to port Xorg, which we're basically almost done. We just have some bugs to iron through. And after that, the goal would be to make a RISC-V board in something like a Vision 5 series board. And after that, expanding the existing networking, because right now the network support is pretty bare bones and it supports basically no network cards. Most of the testing is done through loopback devices. If any of you may want to check Ironclad, either download the source code or download the distributions along with the images used for testing and doing this presentation, feel free to go to ironclad.cx and you'll be able to find that there. Before finishing the presentation, I just wanted to say thanks to a few organizations and people that have helped me get on with this project. The first logo represents Savannah, which is a hosting solution provided by the Free Software Foundation, which is where Ironclad is hosted, along with the website and things like bag support tickets and the like. The third logo would be Limine, which is an x86 another bootloader, which also supports other architectures, which was mainly used for x86 code reference, and also for it's the bootloader used for booting Gloar. Along with that, I also wanted to thank Ada Core for making the tools that actually allowed this project to even be possible, to begin with things like NAT-proof, which is used for the formal verification and helping with the whole GCC NAT port. Along with that, I wanted to say thanks to three people that have also helped me a lot with the project. Mitsuki, creator of the Limine bootloader, is also one of the main maintainers of Gloar and helps me a lot of times to try to get software to run. Lucretia, I'm sorry if I'm butchering that name, is the creator of a lot of the creator of basically all of the Ada information about how to get it running on a freestanding system. Not a lot of information out there, and thanks to Lucretia, at least there's some of it. And INAF, which is a new volunteer, which has helped me get Ironclad to an acceptable licensing state, solving all the issues that arise from using the GPL and how to handle licensing in a project like this. And I guess that would be all. If any of you have questions, I'll be happy to take them now. Thank you. Thank you.
Yes, I'm wondering about the compilation options for the non-Spark Ada. Is it compiled with runtime checks enabled?
Yeah, the parts that are formally verified are compiled without runtime checks using the suppress all checks pragma. The parts that are not formally verified or are formally verified to such a level that does not allow to rule out runtime issues is compiled with runtime checks enabled.
Hear me? Can everyone hear
Hello?
me? Sure. I always
Yeah.
have problems on this side for some reason. Hello, can people hear me?
Yeah. Yeah, it's perfectly fine.
Well, people can hear me now. So, yeah, so that was a great presentation. I'm really surprised that you got this far in I think a really short time. A lot of people have attempted to do what you've done, and so, but wow, I really like what I've seen. Out of curiosity, I don't know if you mentioned that. I missed a little bit of the beginning. Did what led you to even take this project on? Because, like I said, a lot of people tried to do something and ultimately end up not getting anywhere.
So hobbyist operating system development is a thing I have done for the longest time. When I got into programming, which must have been the better part of a decade away,
Hello,
I always had. Hello?
hello.
Hello? Oh, I'll continue, I guess. Um, for when I started programming, the first one of the first things I did is always have curiosity about what was in the underlying levels of it, from doing application development that leads you to operating system development. And since then, I have been deep into the hobby operating system community. Once I started learning about Ada, which I did because I have a lot of interest for things like the aerospace industry, one of the natural things to do was to start making an operating system for it. I hope that answers the question.
Oh, yes. Thank you so much.
Well, thanks to you. Sure. Yes. I know about a bit about OS. I have not heard of the second one you have mentioned. How Ironclad compares to it, probably Muen implements an architect. It's basically a hypervisor slash OS. It's a small component that sits and emulates other environments on top of it. Ironclad instead is a whole POSIX experience. All the components, not only the coordinator of these virtual machines that Muen uses, all of it is aiming to be formally verified. It's a whole encompassing experience. It's not a coordinator for other clients. I hope that answers the question. If what I remember about Moen is correct, I have not read about the project in a while. But yeah.
No worries. It does answer the question nonetheless. Then another question I would have is, you said that you're trying to implement XOR into Galore, into Ironclad, and and you use XOR as an example to show what an attack vector could do to an operating system. Have you thought about maybe using newer technologies such as Wayland or newer packages that may potentially lighter to work with?
I would be totally open to using something like Wayland. The issue that we have experienced is that while systems like Wayland are built keeping things like Linux, basically trying to supporting modern technologies only, projects like Xorg, all projects like this have a much easier porting, given that they were originally designed to run on a whole range of POSIX systems. POSIX compatibility is a quite hard thing, and things like Wayland, given that they are designed to work with newer systems and with a smaller selection of systems, oftentimes turn to hard code several interactions between subsystems or stuff like that that has yielded problems in terms of porting. If instead of XOR, Wayland could totally be used, the thing is that that would require quite a bit more of work, given that Wayland, for example, requires libinput, which itself requires UDEF, given that it's meant to work on systems like Linux, which is a big dependency and depends on way more things than what POSIX mandates. While XOR, a part of a frame buffer, it doesn't really require much more. Well, and Unix sockets. So it's basically it's just an approach issue, trying to get the most value for the work that is invested.
Okay, thank you. Yeah, it does answer my question. Yes, Rod.
Can you hear me? Can
Yeah.
you hear me? Yeah.
Yeah.
Hello. I used to read up on what was called Marty OS, Minimal Ada Real-Time Embedded Operating System. It was for x86, and I was just wondering if you were all familiar with that project and whether any of the ideas would be useful to you. That's pretty much the question.
By the name alone, it does not seem familiar to me. It's possible that I have seen it in writing or somewhere else. Ironclad has a lot of inspirations and a lot of operating systems, namely things like QNX, things like Linux, things like FreeRTOS, LinksOS as well. There is a few inspirations in that front. So it's entirely likely that I may have seen it over the development until now and taken some ideas. But by name alone, it does not seem familiar now.
Yeah, okay. Yeah, I was just
If you
curious.
have some, if you have some links, I would love to read about it though. I always love to get more inspiration from other systems. Try to.
It's the project is it is defunct at the moment. Well, has been for several years. I'll just quickly see if I can find the link for you.
Sure, thank
Carry
you.
on.
So Therudan already shared a link in the chat, so if any of you would like to read up on Marte OS, you can. Nonetheless, the links will be in the video description.
Oh,
We will make sure.
I'm so sorry, Martos. Yeah, I don't know why that didn't come across my mind. Yeah, I have heard about Martos. Wow, yeah.
Yeah.
I'm so sorry about that. Yeah, as a matter of fact, I am from Spain, and the fact that it's a Spanish project as well has made me even look more into it. Yeah, some details about scheduling have been inspired by MartyOS deeply. Yeah, especially things like scheduling and how memory management is done. Yeah, I would say those are probably the two biggest things that I have taken inspiration from MartyOS along with other operating systems.
Yeah, I when I first started looking at Martios, I was surprised at how simple an operating system looked when it was written in Ada, as opposed to the hideous mess we get with C. Yeah, so I was just curious to see how you to see if you were aware of that project, and yes, I'm glad to hear you are.
Yeah, it's a
That's
great
enough
project.
of me.
Thank you, Rod. Does anybody else have more questions? Okay, so I wanted to ask one regarding the distribution Galois. Is there an easily
Yeah.
and readily available like ISO that we could load into a virtual machine to give it a spin? Or do we currently need to build it? What's the tool chain required? Or, well, you said that the documentation is in the webpage, but if you could give us a little bit more information here.
Surely. Gloar does indeed ship ready-built images for dropping into either a USB if you want to put it into a physical system or to spin them up in Cameo or other virtualization software. The images come with instructions as well. And in the Ironclad.cx site, in the site navigation bar, you will find a link that goes by download distribution. You can click there and there you will be able to get an image with a few clicks. If what you want is to build the image yourself as well, there is a tool made by Mintsuke, which is called Jinx, which is shipped on the Gloar repository as well, which allows to build it with a simple command.
Okay, thank you. I saw that Max wrote in the chat whether Ironclad has an Ada runtime on top of it, or what do you do for a runtime?
Ironclad, the kernel itself, does ship with its own RTS or runtime system as Ada requires. It's a quite minimal runtime system. It does not implement things like tasking or other really heavy Ada things. It mostly concerns itself purely with rapid the new and free operators. Well, the new operator and then check the location call, along with offering information about the system. But yeah, it's a really small runtime that runs for the kernel. In terms of userland, it has the runtime that GCC ships with for Ada compilation.
Thank you. And another question that was asked earlier in the chat, I would like to read it out. I know you answered it there, but if you would like to expand on it. Someone asked, how do you deal with bad args, since some POSIX functions may use them, and Ada does not allow for variable arguments in function calls?
So most of the details of the userland are first dealt by the libc and the C runtime if it's C code, which by it being bad I mean it's asking about C code, and the kernel is not aware of it whatsoever. Some syscalls traditionally in POSIX, which I imagine is also what the question could go for. Some syscalls in POSIX traditionally take varargs. Things like open may additionally take several arguments at the end to represent things like mode, or things like some variables, some versions of the exec functions may also take variable arguments depending on the version of the function and other factors. In Ironclad, those syscalls are forced to a certain number of arguments. So, for example, the open function will always take a mode. In that way, one can just ignore varars when it comes to jumping into the kernel. Again, in userland, it's completely transparent for the kernel. It's whatever the compiler and the assembly that is generated by said compiler does.
Thank you. Are there any more questions? Yes, Rod?
Just one final quick question. Have you brought up this project on comp.lang.ada for the news group and possibly asked for volunteers or people to help with the project?
I have not posted it in comp.ada. I will surely do so since you recommend it. The project has been mostly advertised in places like r/ada, the subreddit that the language has, and in places like the hobbyist operating system communities. But no, I will surely make sure to post it on the mailing list. Thank you.
Yeah, that would be great. Thanks.
Well, thanks to you.
I see a question in the chat, which is kind of interesting and fun, made by Weston. And it says, what's the largest program that you've been able to run on Ironclad?
Well, the largest program would deceptively probably be a part of it would deceptively probably be NeoFetch, and not because it's an incredibly complex program on itself. NeoFetch, which is just the bash script that is used for posting that system information there in the stream, but because it hammers several facilities of the system really heavily. Think it spawns tons of processes by doing a lot of recursive shells, hammers out of such systems that way. And in terms of dependencies of what it actually takes the program to run, that's a quite heavy program. A part of that, things like GCC, which runs, runs when it wants to, it runs. It has also quite been a challenging port. Let me just do a GCC touch version there. It runs and things like Xorg as well because they pull a lot of things in terms of what is required from the kernel, things like Unix sockets, things like easy interfaces to frame buffer devices and stuff. So it would be either programs like NeoFetch that call a lot of recursive programs a lot and hammer a lot of subsystems that way, or big programs like GCC or XOR, which pull a lot on what the kernel can actually do.
Thank you for your answer. And now that you showed GCC running on Ironclad, are you trying to make it self-sustainable and develop Ironclad within Ironclad?
It's definitely something in the horizon. It would definitely be possible to do so. I'm mostly right now focused on getting XOR to run, but yeah, I imagine that with minimal work that would be possible. I would need to port GPR build, which is not ported yet. Make is ported, and it uses make. So yeah, that could definitely be possible.
Thank you. That's very cool.
Yeah.
So, are there any more questions? Let me take a look at the time. Oh, okay. We've been running for like 45 minutes already. That's pretty good. Okay, then Strixu. Sorry, I didn't get your name. So how are you called?
I'm called Christian, but I go in the
Christian.
internet by Strixu. Yeah.
Okay, thank you very much, Kristen. If anybody has any more questions or would like to know more, please go to the webpage, the main webpage of the project. It will be posted within the video description in YouTube, and I will make a short summary of this meetup in the normal channels like com.Ada and the forums. And yeah, if I will stop the recording now, unless anybody has some final remarks. However, I see that Dirk is here, and if anybody is interested in discussing some FOSDEM topics, please stay here for like four or 5 more minutes. And then, yeah, if anybody has some final remarks, please, this is the time.
Before leaving, I just wanted to say thanks for everyone for showing here. It has really been real nice to be able to share the project with the wider data community. And I hope to show progress soon. Maybe, who knows, maybe we do another presentation with XOR running. That would be cool.
Then thank you, Christian. Thank you, everybody, for coming. It has been a very nice meetup, in my humble opinion. Hopefully you share it. And we should be seeing, we should be having the next one in December. I don't think that should be a problem to anybody, at least not to me. So thank you very much, and I will see you soon. And once again, if you want to stay here for the first minutes,